So I will continue from the last point where we have talked in our previous lecture, and we have said that we can do linear interpolation for the tables. And if you have two values in the table, so for example, we had the value for 500 degrees Celsius, 600, and another we didn't have any intermediate value. And we assume that the points that is between these 500 and 600 has a linear graph. And from that linear graph, the slopes should be the same, whether you take this point or whether you take that point. And due to that slope, you can find the value of the enthalpy for that intermediate temperature value. Okay. So this one was from the previous lecture. Now I'm going to solve some more example about the tables. So the first example is that we should find the enthalpy of refrigerant. So this one, you should look for the table at the 0.24 megapascals, and according to the given value below. So according to the given below. So firstly, it should be dry saturated vapor, then it should be wet saturated liquid, and then with moisture content of 10% at 50 degrees Celsius, at 55 degrees Celsius. So therefore, I should add one more stuff here that I'm going to talk about is the quality. So I will add the quality here so that I will talk about what quality is, and then I'm going to solve this example. So the quality, it is shown with the letter X. Okay. So I will just give the water example, which is the easiest one to understand the topic. Say that you have a water at 100 degrees Celsius and you are heating it, so you are giving heat, and inside this vessel you have 1 kilogram of water. So you have 1 kg of water, and some part of it, say that let me put some, so 0.2 kg, and this part is 0.8 kg, and the 0.2 kg of the water is vapor. This one is vapor, and the 0.8 kg is liquid. And when we introduce the quality, and the quality means that how much, it at the end shows the name says it, so it shows the quality of the fluid, because more vapor means more quality means more energy. So here you have the amount of the vapor, mass of the vapor divided by the mass, total mass. And here you have the 0.2 kg vapor divided by the total mass, and it will make 0.2 or 20%. Okay. There is 20% quality, or the 0.20% of the total mass is the vapor. This is just a simple equation. You can get the rest. So if I draw it on a TNU diagram, if I draw it, so if you remember, there had in the TNU diagram we had the saturated liquid line. Let me draw it again, this part. We had the saturated liquid line in TNU diagram, and we had the saturated vapor line in TNU diagram. And what we are interested in, the water at the 1 kg, so sorry, water at 100 degrees Celsius. So this part is what we are interested in. It is 100 degrees Celsius, and the rest is superheated, and this part is it's compressed. Okay, so this region is compressed, and this point here is the nu F, or this point here is nu G or UG, it doesn't matter, HG. Similarly here, nu HG, UG, okay, etc. So if you are here, so if you are at the F point, here the quality is 1. Here at the F point, the quality of the water is 0. Here you don't have any quality. X is 0 because it is only liquid. And if you are at the next extreme value, which is the G value, here you have the quality as 1 because it is only vapor. It's only vapor here. It is only liquid at the nu F value. And then it is not defined at this superheated region because a superheated region is only vapor, therefore quality is not defined here. So if I am at some midpoint here, so let's first talk about our example, and also let me show the temperature value here. It's 100 degrees Celsius. And for our example, the quality is 0.2, and it means that we are almost here. So 0.2, so the quality is here, 0.2 or 20%. Okay, so this one is the definition of the quality. And you can also extend this definition of the quality for all of the properties. For example, if you say that I'm trying to find the new value, if I have the quality value, so it will be that nu F, the first value here, plus the quality multiplied with the nu G minus nu F. So in simple terms, it means that the first point plus the difference in this nu G and the nu F, the distance multiplied with the fraction. It is what it says here. So the first point, this one, plus the total length multiplied with the fraction. Similarly, you can find the enthalpy value if you know the quality here. So enthalpy will be HF, X times Hg minus HF, or if you are interested in the U value, for example, you can find the internal energy, you can find U is UF plus X into UG minus UF. Similarly, for any property, so you can find the YF, so Y will be equal to YF plus X times YG minus YF. This is the equation that we are going to use, and we will find the properties with given quality values. Okay. So now let's go back to our example and solve it. If you know what quality means. So firstly, we will find the dry saturated vapor. So here, dry means, so it has a quality of 1. Okay. Here, the wet saturated liquid means that wet means it has a quality of 0. So this part means it has quality of 0 with moisture content of 10%. So here you have the moisture content. It will be 1 minus quality. Okay, because the quality shows the vapor content, so this one shows the vapor content. Therefore, the moisture content will be opposite of it. So here, therefore, you will have 90% of quality. Okay, so then at 50 degrees Celsius, this is the next one, and the 54. Let me firstly open the table and to find the values there. Okay, so if I go back to the table values, so let's see. I should firstly go to the refrigerant 134A at 0.24 megapascals. So I should look for this one. Okay. So the list of the tables, so it will be that. So you can see the list of the tables. So we have the A4, A5, A6. It is only for water. You can see the water value here. or it can be water here, and it's also water, and it's also water here, and the water here. And what I'm looking for is the refrigerant, so R134A, you can see. So now, therefore, I should move on to A11 or A12. So I will see which one is okay for me, because here you have the pressure value given only, so therefore I should use this second one. Because you can see second one is arranged with respect to pressure, and the A11 is designed with respect to temperature. Since the question gives the pressure value, therefore I should look for the A12, the table A12, and let's solve it for the table A12. Okay. Now let's go back to table A12. Okay, A12, so we have the water here, no problem. Then we are going to refrigerant. Okay, so refrigerant, and we are looking for the pressure table, okay, because the saturated refrigerant table, it doesn't matter whether it is temperature or it is pressure. If you look at the temperature table, you can see that the temperature is preferred one. So here you have good values, for example, 20, 22, increments are good. But for the pressure value, you see the pressure table, pressure is the preferred one. So you have the 60, 70, 80. If you look at the temperature values, it is not, so it doesn't have good increments. So you can see there are fractions here. Therefore, for our problem, so that the pressure value is given, it is 0.24 megapascals, it means that it is 240 kilopascals, and I'm trying to find the enthalpy value. If it is, quality has 1. So if the quality is 1, so you remember from the chart here you have the 1 quality, it means that we are looking for the Hg, and here quality is 0, you are looking for Hf. So firstly, for 240 kilopascals, this one, this is the line, and I'm looking for the Hg. The first one is Hg, okay. So Hg line is here, saturated vapor, Hg, and it makes 247.28. The first one makes 247.28 kilojoules per kilogram. Now comes the HF one. HF is it will be the first one, which is 44.66. Will be 44.66 kilojoules per kilogram. This is the HF, and this is the Hg. Then I will solve the C part, which says that find with the quality of 90%. So it will be H value that I'm trying to find will be HF plus X times Hg minus HF. Okay. So if you remember, we have said that Hg minus HF, this one is HFG, it is given in table. Okay, so it is given in table, therefore I will just write HF plus X into HFG. And the HF value is here, I've taken it from the table, which is 44.66 plus the quality is 90%, therefore 0.9, multiplied with the HFG, and the HFG is, I said it is given in the table, it is 202.62, but at the end it is the difference between Hg and the HF. It is 202.62 kilojoules per kilogram. And from here, you can find the value of the H enthalpy. If you have the value, you can tell me that I can write it. Okay, then, so if you find it, then you can go to the next part of it. So this is just the numerical value. You can tell me whenever you have found it. So that next one will be that 50 degrees Celsius. For 50 degrees Celsius, you will have the refrigerant, the enthalpy of the refrigerant. The pressure is the same. You have the pressure at 240 kilopascals, but the temperature is different now. The temperature is 50 degrees Celsius. If you remember, we have said in our previous lecture that first of all, we should check saturated table. The first step is saturated table. Okay. So if it is in saturated table region, if it is not in saturated table region, then it means that it should be either in superheated or the compressed. So let's have a look at here. So at 240 degrees Celsius, the boiling temperature of refrigerant is negative. Let me write it here. So at pressure of 240 kilopascals, T saturated is negative 5.38 degrees Celsius. So you can see the lower value of the temperature. So if it is 50 degrees Celsius, then it means that this one, if it is more than that one, it means that it is superheated. If you remember, we have solved the examples about this one, it is superheated. Okay. Since it is superheated, the temperature is too high, then you should go to the superheated table. Now let's go to the superheated table and find the value of it. So saturated refrigerant superheated table. So I'm looking for 0.24 megapascals. So this one is here, 0.24 megapascals. And I'm looking also for H value. H, you can see the enthalpy. This one is the enthalpy, and this is the table part that I'm looking for. And the temperature is the 50 degrees Celsius. This one is 50. This line. Okay, for this line, the enthalpy value is in this column, so that 296.08. You can see for 50 degrees Celsius line, the row, okay, for this row, the column for enthalpy is this part, which is 296, and the pressure is the important one because you have to look for the table for the pressure 0.24 megapascals. Okay. So if I do that, I will get from the table value A13, the enthalpy becomes 296.08 kilojoules per kilogram. Okay. Now comes the 55 degrees Celsius part. So now we solve it for 55 degrees Celsius, and if you remember, we have said that we are going to use the linear interpolation if it is not in the table. I'm looking for the table for 55 degrees Celsius, and you see that there is 50 degrees Celsius, there is 60 degrees Celsius, but there is no 55. Therefore, I will just do the linear interpolation. On one side, you will have the enthalpy, and on the other side, you will have the temperature. And for the temperature value of 50 degrees Celsius, the enthalpy is 296.08. Okay. For the next temperature value, which is the 60, given in the table, until 60 degrees Celsius, this is this line. It is 305. Let me draw it actually. So it is the 305.23 kilojoules per kilogram. That is for the next point, which is theta. What I'm interested in is the mid-range, but firstly, I will assume that the temperature the properties change linearly, enthalpy versus temperature change linearly. This graph, so then I will do this one is linear interpolation. Okay, if it is higher order interpolation, then you will assume higher order graphs, higher order charts. Okay, then the point that I'm interested in, the 55 degrees Celsius, it should be here, and this point will fall here, so that you will just work out with the slope. Slope will say that this one, 23, minus the initial point divided by 60 minus 50. Okay, this one should be equal to the value that I'm looking for here, which is x. So x minus again the slope, which is 296.08, divided by then the similar temperature difference, 55 minus You can work it out and find the value of x, and we can finish the example. Okay, so if you have the values, you can tell me. So yes, Suleiman has found the first one, which is 200. Let me see. It's 227.01. It is kilojoules per kilogram. And for the second one, Rajab, 300.6 kilojoules per kilogram. Okay. So I have finished this example. So now let's move on to the next example here. The example says that to determine the specific volume, enthalpy, and internal energy of the compressed liquid at 10 megapascals and 330 degrees Celsius, 300 degrees Celsius using compressed liquid table, saturated water table using same pressure and temperature. Find the error. Explain the reason why the properties aren't so different. When do we think that the value will be different and why? So the question says that we have a pressure of 10 megapascals and we have the temperature of 300 degrees Celsius. These are given. And it says that to find the specific volume and the enthalpy and internal energy of the compressed liquid. So the question itself says it is compressed, but you can check by yourself how you will do that. You can check. So as always, looking at saturated table. The saturated table, it is the first step. As always says, it is the first step. You look at it and then determine the region, if it is compressed or superheated. Question says that find the value of the nu, h, and the u with these given values. Okay, then use different methods, and the method says that use saturated water table instead of the original table, which is the compressed liquid table. But now let's find it and then do the next step. So firstly, you will use the compressed water table. This will be the first step. Okay. Now I'm going to the, firstly, if you can check it, actually it is compressed or not. So I can move on to any saturated water table with respect to temperature or pressure. So I will use the temperature value here, which is 300 degrees Celsius, and I'm going to saturated water. So it is about A4 and A5. So that for 300 degrees Celsius, you can see it here. The pressure, saturation pressure is 8,000. Let me write it here for saturated table. This is the step that I'm going to use. So if the temperature is 300 degrees Celsius and the saturation pressure is 8,000, so let me write it, 8587.9 kilopascals. You can see the pressure is more, therefore it is compressed. You can check it. So the P is more than P sat, therefore it is compressed. Okay. Now compressed water table. I should go to the compressed water table. So this one was the saturated. I should move up the tables here. Compressed, superheated. We are in superheated now. You can see that. Now compressed liquid table, compressed liquid water, which is 87. I'm interested in 10 megapascals, so 10 megapascal is here. And I'm interested in 300 degrees Celsius. And the 300 degrees Celsius, you can see. this line. So I will take the values from this line, firstly the new f and then the uf and the hf. So from A7, the new value, u value, sorry, this one is compressed as u value and the h value. That the new value is 0.00 13908. So 13980, good. So this one is the meter cubes per kilogram. And the next value is the u value. And then you have the h value, which is 1343.3. Okay. These are the values by using the compressed liquid table. So these ones are the correct ones. Okay. Now I'm going to find the values. Instead of using compressed liquid, it is characteristic to compressed liquid only. I'm going to use the saturated water table. Okay, but in one case, I will look at the pressure, which is given here. In the second case, I will look at the temperature. Okay. Now let's do it. Okay, so now I will assume values by saturated region. Okay, so firstly, I will take the P as I will work with the P value, which is 10 megapascals. Okay, now let's go to the chart here. And the chart that I'm going to use is the saturated water table, but with the pressure, which is A5. So A5. So I will take the new F values, okay, not the mixture, but new F. So that new F, UF, and the HF. This is what the question says, okay? I'm doing what the question says to me. Okay. This one is the temperature, and here you have the pressure, and for that pressure value, I'm interested in 10,000 kilopascals, which is this line. Okay, and I will first take the new F value, which is 0.01452, so 0.001452 meter cubes per kilogram. And the UF value is this line, which is 1393.3 kilojoules per kilogram. And the HF value is that this one is the HF. You can see the column here. So this one is HF, this one is the UF. And see the column. So it is 1407.8. So it is 1407.8 kilojoules per kilogram. Okay, I've done it, no problem. Now comes the last step. So in this case, I will again use the assume values. I will assume values by saturated region, but instead of working with the pressure values, I will work with the temperature value, which is the 300 degrees Celsius. And therefore, I will use the table A4. Okay. Now I will go to table A4. So that for table A4, the temperature of 300 degrees Celsius, let's have a look at it. So temperature of 300 degrees Celsius. This is the temperature. So these are the rows that I'm going to use. And I will first look at the HF value, which is the 0.001404. So new F is 0.001404. And the UF value is so 1332.7 kilojoules per kilogram. And this one is meter cubes per kilogram. And then HF value, which is the last one, which is 1344.8. 1344.8 kilojoules per kilogram. Now you can now compare the values. Okay, I finished this part so that you can compare the values. And when you compare the value, the compressed table with this one and with that one. Let's first start with the new values. For the new values, this one is the 1398, this one is 1452, and this one is at 1404. You see that this one is close. This one is very wrong with respect to that one, but this one is very close to that value. Next value, 29, it ends. Now this one is 93, and this one is 32. You see, it is very, very close. UF values, they are almost the same. And H value, this one is again wrong, and this one is 44, and it is 43, and it's almost the same, okay? Here you have the small error, so small error. Here you have the large error. The reason is that, so let's now move on to why the reason. Why do we have errors? In one case it is small, and in second case it is large. So I'm looking for the temperature pressure value. So let me erase this one. This one is the temperature, and this one is the specific volume. And this is the curve, if you remember the famous curve, the dome-shaped. Okay. And you have, so that I will take the first 10 megapascals here. It is the pressure is 10 megapascal. And for this pressure value, when the pressure is 10 megapascal, I will just write the saturation temperature. It is from the chart. Okay, I'm going to the chart and I write the saturation temperature for the 10 megapascals. If it is 10 megapascal, saturation temperature is at 311. So this part, boiling part, it is 311.00. So it is 311 at the end. Degrees Celsius, this line. Okay. Now I'm moving on the next line here. So I've used the 300 degrees Celsius, so you can look at it. So I will go back to the 300 degrees Celsius. What is the saturation pressure for 300 degrees Celsius? You can see the saturation pressure is 8587.9. So it will be next line. Let me draw it next line here. So it is. So I have used this one. It is that 300 degrees Celsius. This one was the second. Okay, in the first step, you see, I have used 10 megapascal saturation pressure region. Now I've used then second, 300 degrees Celsius. I'm just looking at what is the pressure for that 300 degrees Celsius. The pressure here, it is 8587.9 megapascals. No. It is 8.6 megapascals. Or if you write it 8.5786 megapascal. It's just, I've just rounded it. Okay, then what I'm looking for is that I'm looking for the real value is that the pressure is 10 megapascals and the temperature is 300 degrees Celsius. I'm looking for this one, which is 300 degrees Celsius. This is the temperature that I'm looking for, and I'm looking for the pressure is 10 megapascals. Okay, this is compressed region. Okay, I'm somewhere around here. Okay, this is compressed region. Temperature is this one, and at some point here, I'm looking for the value of the value of the nu, h, u, etc. So this part is the compressed region. Okay. In one case, I have taken the value here. So it was the first case. Okay, I have taken the value nu f, u f, and the hf for 10 megapascal values. I've taken it here. So this is the first case. And in the second case, I have taken the values at 300 degrees Celsius. So in the second case, I have kept the temperature constant and I've taken the values here. This is the second case. Okay, But the real value is somewhere around here. So I don't know where it is. It is, yes, it is the intersection of 10 megapascals. Let's say it is here. This one is the real. The real one is here. The assumption is, second assumption is here, and the first assumption is here. So if you look at the values, you can see that this one is the real one, new real. This one is the second assumption, new second assumption, and this one is the first assumption, new first. So you can see the second assumption is very close to the real one. So this is the second assumption. You can see the error, and the third assumption is far away from the real one. You can see this one is the large error, and this one is the small error. Okay. So why do we have the errors? The reason is, so if you keep the temp pressure constant, so in the first case you have done it, you have kept the pressure constant, but the temperature has changed to 311 degrees Celsius. In the second case, you have kept the temperature constant, which is 300 degrees Celsius here, but you didn't play with the pressure. Okay, so when you keep the pressure constant, the temperature changes, but you should remember that water, so it depends. The water depends on temperature more than the pressure. So it means that its values change with temperature fastly. Okay, values change with if you have the change in temperature, the values change faster than due to change in pressure. Okay. In the second case, you can see I haven't changed the temperature. Temperature was the same, therefore the values didn't change a lot. But in the first case, I have changed the pressure, so but the temperature has changed. But here, due to change of temperature, so you had the large errors. So here, so I've kept the pressure constant, so P constant, but T changed. But in the second case, I have kept the T constant, but P changed. Okay. Since in the first case, P was constant, the T didn't change, T changed, therefore there was a large error. But in the second case, I've kept the temperature constant, but only P changed, pressure changed, therefore I did have the small error here. Okay, so I'm moving on the next example. So the next part of our lecture, which will be the boundary work. So if you have questions till now, you can ask. Otherwise, I'm moving on the new lecture, which is the boundary work. So that nobody has a question. Okay, so I'm going on the new part of our lecture, which is the boundary work. So that boundary work is, this is our piston, and there is a heat source. The heat source, so if you add the heat, so the piston dimensions will, so the piston will move upwards, okay, because you are adding heat, the volume will change, so it will expand. Okay. And as it expands, as this one expands, it does work on the environment. Okay, it will expand and do work on the environment. Yes, sir. So let's say that after some time you have reached the point here. The piston reaches here. So, and it moves a distance of dx. Okay, and inside the piston here you have the gas. Here you have the gas or any fluid. So this fluid applies some pressure on it. So it can, let me raise the gas part here. Let's say that this fluid here. So this fluid applies some pressure on it. So it has some pressure that applies on it. This one has a pressure of P. Okay. So if you look at the force analysis here, the force, The force will be that pressure multiplied with the area of the piston. Okay. So the piston, this one is actually a circular piston, and then you will have the pi d squared by 4. This is the force. And then if you are looking for the work, so that work will be the force into the distance. Okay. And in our case, it will be that pressure into the area of the piston and multiplied with the dx. Area of this piston is here, overall area, and multiplied with the dx. Okay, and I can write the pressure as a separate term and the area of the piston and multiplied with dx. Okay. And this one, the area piston dx will be small volume, which is PdV. And this PdV is not the integral form, it is differential work. Add it, it is differential work. Okay, it is differential work, and the differential work means that here you have the change of boundaries, but the boundary changes slightly. Okay, so now, so that say that this was the initial boundaries. You can see these are initial boundary. But after some time, you will have after some time, I've said it, you will have this boundary. Okay, you can say the boundary, this one was the initial boundary. And the second one was the final, let's say intermediate, okay, or the second boundary. So you can see that the boundaries has moved, okay, the boundary of your system has moved at any distance and at any new location, and therefore it is the boundary work done by the boundary, and it will be equal to PdV work, okay, pressure into the small change in volume. But if you are trying to find not the differential work, but if you are trying to find the integral work, or if you are trying to find the total work, it will be that you should integrate PdV with respect to from volume 1 to volume 2. Okay. That will be the work done by the boundary. Okay. So where do we see this work? This one is so you can see this kind of work. I can give you one example, which is the car engine. Okay. In car engine, the piston moves up and down. The piston moves up and down, and you have the change in volume, and the pressure into that change of volume will be that V1 into V2, and you will have the boundary work. Okay, so I can give one simple example from the daily life, is that the syringe. Okay, in syringe, so this one is the syringe. Okay, and inside that syringe you have the piston here, and that piston moves up and down. Okay, this piston it moves up and down, and therefore you have the boundary work. Okay, this one is just a simple example. The real one is the car engine. You have the changing dimensions or change in boundary. Okay, whenever you have the change in boundary, you have the boundary work. It is very famous for the closed systems. For open systems, the boundary is almost fixed. It doesn't change a lot. But for closed systems, the boundary changes, and therefore we have the work done by the system on the environment. Okay. So with this one, there will be a question for you. So the question says that we have 2 kilograms of steam at 1 megapascal, 2 kilograms of steam at 1 megapascal, and the 300 degrees Celsius inside the piston cylinder configuration shown below. So at this location here, you have the 2 kilogram, and the pressure is 1 megapascal, and the temperature is 300 degrees Celsius. And then the cross-sectional area, of course, the area of the piston is 0.2 meters squared. This is the cross-sectional area, the piston. The spring coefficient, you have the spring here. It has a coefficient of K value, which is the 200 kilonewtons per meter. Okay, this is the spring coefficient. And it is at the beginning of the process. The configuration shown is below for the beginning of the process. And then the steam is cooled. Okay, okay, and this steam, you can see it is at high temperature, 300 degrees Celsius. It is then cooled. As it cools, the system boundary changes, okay, the piston moves down, this one moves down, and the spring becomes compressed. So then it touches the spring, and then the spring becomes compressed. But till some distance here, you can see, for that distance, there is no any, so that the piston doesn't touch the spring. But after some distance, 0.5 meters, it touches it. As further cooling is done, the system pressure drops to its final value of 500 kilopascal. This one is the P final. Now you can see, so when you cool the system, the piston moves to a new location here, and then as you further cool it, it compresses the spring here and rests on these stoppers here. You can see the stopper, one side and on the other side. The stoppers and the piston rests on it. You can neglect the volume of the spring, you can neglect it, and the stoppers. So it's not so important. Calculate the system temperature of liquid vapor when the piston touches the spring. This is the first step. And then the quality, pressure, and temperature of the system when the piston stops on the stopper. Calculate the work done by the gas spring arrangement. Calculate the amount of heat interaction. Show the process on a 2-unit diagram. Okay, these are the questions that we are going to answer for. So firstly, I will write the energy balance, so the free body diagram on the piston. So this is our piston. Okay, and this one, the FBD, this one is till spring. Okay, it is only till the spring, but after the spring, the free body diagram will be different. You will have the additional force here. Okay, so the free body diagram till the spring, you have the mass of the piston, which is the free body diagram of piston. You have the weight of the piston, which is W, and you have the pressure by the environment on the piston, which is PATM. Let me write it here, so that you have the PATM here. So they should have the same values. So I will extend the lines here. So PATM, and inside the piston, so that inside the arrangement here, you have the pressure by the gas. Okay. If you write the free body diagram, it will be that pressure of the gas will be equal to W plus PATM. Okay, so W of the piston is constant, PATM is constant, and the P gas is constant. Okay, so what it means is that as the dimensions change from the initial point, which is here, and then when you move on the next point to this one, the pressure remains constant. It doesn't change. Okay. This is the first value that is important for us. And there is another value that is constant, which is the mass. Mass is constant because it is a closed system. Mass is constant, but it is always constant, not dependent on whether it touches the spring or stoppers. Okay, now let's solve it. So firstly, we should find the properties that we can use in table. Okay, so in tables, what we have, so these thermodynamic questions are solved by using the tables. In tables, we have the temperature, saturation, we have the pressure, saturation, or you can have the temperature, pressure itself. You have the U, nu, H. Okay, these are the values that are going to use in tables. Okay. So in this question, what we can do is that the mass of the steam is given, which is 2 kilograms. Okay, and I can find the initial volume because so from this initial volume and the initial mass, I can find the new initial. Okay, and then you can find also the new final when it touches the spring, and then from that value you can find the temperature of the liquid vapor. Okay, now let's start. Okay, so that the initial volume here, so values, so you have 0.5, 0.8, so you don't have any value to find the initial volume. Therefore, this one is a problem. So it doesn't help us to find the initial volume. But what you can do is that instead of using the mass and the volume relationship, you can find the initial volume from these values, which is 1 megapascal, 300 degrees Celsius. One is 1 megapascal of pressure and 300 degrees Celsius of temperature. If you use these temperature and pressure values, you can find the initial nu from the table. And to find it, first you should determine whether it is superheated or saturated or compressed. Okay, therefore, the first step is look at the saturated table. We should look at saturated table and determine whether it is in which region is this one, and then we can find the value of the nu. So I will open the table now. So that in that table, so I'm looking for you can look at the saturated water with the temperature or the pressure. So I'm looking for the temperature value, which is 300 degrees Celsius. For the 300 degrees Celsius, you can see that the pressure is 8,587.9, but in our case, the pressure is at 1 megapascal or 1000 kilopascals. In the question it is 1000 kilopascals, but here it is 8,000 kilopascals. So it seems that since our pressure is less than the pressure value given in the table, then it means that we should look at the superheated region. Okay, so therefore we should go to the superheated region because this pressure is more than the pressure that is given in the question. So that I should go to the superheated region. This one is saturated, and then superheated water table. So I should look at the pressure of 1 megapascal. So this one is 0.1, 0.8, and the 1 megapascal. And I should look at the temperature of the 300 degrees Celsius. You can see the temperature value here. The 300 degrees Celsius temperature, it gives the specific volume of 0.25. So it is 0.25799 meter cubes per kilogram. Okay. Now I'm moving on to back to our example. So we have 4 minutes. Okay, so in 4 minutes I can finish this part of the example. Okay, so I have found the specific volume, which is 0.25799 meter cubes per kilogram. This is the initial specific volume, but so this one is the initial specific volume. So I know the initial specific volume, I know the pressure and the temperature. So, but I know also that, so let me go back here. So mass is 3 kilograms and the initial specific volume is 0.25799. Okay, so from here I can find the volume. Okay, total volume, you can find it. It will be that, if you remember, this one has a meter cubes per kilogram, and it will be that nu initial into m. Okay, this one will be the total volume here, but when it touches the spring here, when it touches, you will have the decrease in volume, which is the delta V. The delta V spring. Okay, then the delta V spring, so you can calculate this value and tell me, so this one will be 2 times 0.25799. And the delta V will be equal to, so that the height, which is 0.5 meters, multiplied with the piston area, which is 0.2 meters squared. It is given in the question. So that delta V will be piston area multiplied with the height. Piston area is 0.2 meters squared, and the height will be 0.5 meters. From here, you can find the change in volume. So you can tell the values here. And the last step will be, so that V total minus the delta V will be the volume. So that volume when piston is on spring. When piston is on spring, you can find the volume here. So that I will just write the steps. I will continue in our next lecture. From the volume piston, when the piston is on the spring, you can find the volume here. And then since the mass is constant, you can find the piston. When the piston is on spring, you can find the specific volume by dividing this one, piston on spring, on the mass. You can find, so you will have the one more variable here, and also I know that P is constant, so it will be equal to that P when the piston is on spring. Okay. So I know the second property, and I can find the temperature value here from table. So I will continue from this part on our next lecture, so I'm stopping the recording now.